Okay, in this video, we're going to work some problems on the subject of maximum and minimum values of functions. So global and local maximum and minimums. And as we talked about when we went through the textbook section on this topic, being able to identify local and global maximum and minimums is important to be able to do, right? If you have a function that's modeling something in real life, you may want to know local or global maximum and minimums. And this might seem trivial, like in other words, why do we need to have a section that talks about this? I mean, just if you need the local or global maximum or minimums, just go find them. Look at the function on paper or maybe plot the function and just go find the local or global maximum and minimums. But the thing is, we need to have foolproof ways of doing these kinds of things in math. So for example, if we're given a function and we want to find global or local maximums or minimums, we want to be sure that the method we use is foolproof. We don't miss any values, or we don't accidentally get the wrong value, right? So that's why when we went through the textbook section, there were theorems that were laid out. And based on these theorems, these more official methods for finding, like, the global maximum or minimum. And that's a proven foolproof method that will work every time for any function. Okay, so let's get started with these problems and we can practice what we learned in this section. All right, for each of the numbers a, b, c, d, r, and s, state whether the function whose graph is shown has an absolute maximum or minimum, a local maximum or minimum, or neither a maximum nor a minimum. Okay, point A. This is an endpoint, and endpoints can potentially be global maxes or mins, but they can't be local maxes or mins. They could be global maxes or mins because the only thing a global max or min specifies is that the value of the function at that point, is it greater than or equal to all other values or less than or equal to all other values? So for the endpoint, as long as the function exists at the endpoint, and it does here, then it could potentially be a global max or min. But here we can see it's neither a global max or min. Okay, so, but it also can't be a local max or min because you can't specify an open interval around this point. You can have an open interval point here, but you can't do anything over here. So point A is neither a max nor a min, any kind, local or global. Okay, point B. This is not a global max or min, we can see, but it is a local min. Why is that? Because we can specify an open interval. That's important. The definition of a local max or min, you can specify an open interval, open, around the point, and within that interval, the value of the function at point B is less than or equal to all other values within that open interval. So this is a local min. Okay, this is it's not a global max or min because it's not the absolute largest or smallest value on this interval, but it is a local max because we can specify an open interval around this point, and the value at C is greater than or equal to all the values within that open interval. Okay, point D. It's not a global max or min. What about local? It can't be a local max or min either. Why is that? Because we cannot specify an open interval around this point to where it's the largest or smallest value. The f of d is larger or smaller than all values within that interval. You might say, well, why can't we say the interval from d to here? Right? It's the largest value. No, for local maxes or mins, the interval is an open interval. So if this is open, then this is not including the value at d, the function at d. Okay, here, this is another local min, but it's also a global min as well, right? This is the lowest value for this entire function. So this is both a local and global minimum. Okay, here, this is an endpoint, so this can't be a local max or min, but it can be a global max or min, and it is the global max. Okay, same problem. This is an endpoint, and it is also the local min. Point A. Point A is an endpoint, and it's also the global minimum. All right. Point B. This is not a global max or min. What about, is this a local min? So let's specify an open interval around this point. Within this open interval is the value of the function at point B less than or equal to all values of the function within that interval. Well, it looks like it could be less than, but the function doesn't exist at this point. So this is not a local or global max or min. Point C. This is not a global max or min, but it's not a local max or min either. Well, here's an open interval around the point. We can specify an open interval, but no matter what open interval we select, there's always going to be values of the function that are either greater than or less than the value of the function at point C. Now you might say, well, couldn't we specify this open interval? No, this open circle is at point C. So then with the open interval, we wouldn't even be including point C. We have to come to the left of point C. Point D, it's not a global max or min, but it is a local min. Point R, local max. And the global max, actually. So both the local max and global max. Here's the global min, here's the global max. S, this is an endpoint, so it can't be a local max or min, but it also isn't a global max or min. Use the graph to state the absolute and local maximum and minimum values of the function. So this is just like the previous problems, except now we're going to be specifying actual numbers. Okay, let's start with global maxes and mins. There is no global min here. The reason is because, okay, if the function existed here, it doesn't, there's an open circle, right? But if it existed, that would be the global min. But since it doesn't exist, there's no specific number we could specify as the global min, right? Because like you could get infinitely close to this point. So you can't specify a specific number. The best you could do is say like the limit. What is the limit as x approaches, this is 1, 2, 3, 4, 5, 6. As x approaches 6 from the left is 1. That's the best you could specify. But there is no global min. Global max, here's the global max. And it's also a local max. 1, 2, 3, 4, 5. So the global max is equal to 5. The global min does not exist. Now, local mins and maxes. Let's start with the easy ones. This is a local min, right? So local, we'll do this. Local min. And then local max. So local min at f of 2 is equal to 2, right? Local max at f of 1, 2, 3, 4. F of 4 is equal to 1, 2, 3, 4, 5. All right, now here's another local value. This is a local min at f of 1, 2, 3, 4, 5. At f of 5 is equal to 3. Okay, those are the easier ones. The ones that are more tricky, what about this? Is this a local max or min? I guess it would be, is this a local min? Think about the definition of local max or min. You specify an open interval around that point, so any open interval is the value of the function at that point greater than or equal to every value within that open interval, or less than or equal to every value within that open interval. Yeah, here it's less than. So f of 1 is equal to 1, 2, 3. Okay, what else? What about here? Let's specify an open interval around this point. And yeah, it's the value of the function here is greater than or equal to all values within that open interval. So 1, 2, 3, 4, 5, 6. F of 6 is equal to 1, 2, 3, 4. All right, same problem. Let's start with the global and local maxes and mins. So There is no global max because you just can't specify a specific number, right? This is an open circle. So global max does not exist. Okay, global min, here's the global min. It's also a local min. So global min is equal to 1, 2, 3, 4 is, well, we'll just put 1. F of 4 is equal to 1. All right. Local maxes and mins. Here, open interval, that is a local min, right? So okay, f of 2 is equal to 2. Okay, here is a local max. F of 1, 2, 3 is equal to 1, 2, 3, 4. Okay, here is a local min. It's also the global min. So f of 4 is equal to 1. All right, and here is a local max. 1, 2, 3, 4, 5, 6. F of 6 is equal to 3. All right, sketch the graph of a function f that is continuous on the closed interval from 1 to 5 and has the given properties. All right, so the first question for this question here, first problem. Absolute maximum at 5, absolute minimum at 2, local max at 3, local min at 2 and 4. All right, so we're doing 0, 1, 2, 3, 4, 5. Okay, so the requirements are that the function has to be continuous on the closed interval from 1 to 5. Continuous. Doesn't say differentiable, so it's not like it has to be a smooth curve. Just continuous, though. At 5, it'll have an absolute maximum, so let's just put this up here. Right, it's closed intervals. The function's going to exist there. Absolute minimum at 2, so let's put a closed circle here. The function's going to have to come through here somewhere. It could be anywhere. Just, it doesn't have to be negative, but we're just going to put it negative. Local max at 3 and local min at 2 and 4. Okay, so it's going to have both a global and a local min at 2, and then just a local min at, or local max at 3 and local min at 4. So when it comes to local maxes or mins, remember there's only 2 types of these. You can have one that's like a peak or a valley, right? Like that would be a local max. That would be a local min. Or you could have, in those 2 cases, the function is differentiable and the derivative is equal to 0. Or you could have a case like this. There's a local min. There's a local max. But there the derivative doesn't exist, but it's still continuous, right? So we can put whatever we want. For the locals, we can make it either a smooth curve or like a kink point. So let's do a kink point here. All right. And then at a local minimum at 4, 1, 2, 3, 4. So, okay, but then a local max at 3. All right, so wait up. Let me do, well, no, okay. A local max at 3, a local min at 4. Well, no, it would be, and then like that. Well, let me try and draw this better. Right? And then, so we've got the local max at 3, local min at 4, local min at 2, and global min at 2, absolute max at 5, and then at 1, just needs to be, the function is defined. So like that, but I'm not going to make it well, it wouldn't matter anyway, but yeah, the function's just defined there. I was going to say I'm not going to make it like do this, make it like a local min or local max, but that technically wouldn't matter. This would still be just an endpoint, not a local max or min. So that's fine. So this satisfies all the requirements. All right, same problem, but now we want to have an absolute max at 2, absolute min at 5. 4 is a critical number, but there is no local max or minimum there. All right. So 1, 2, 3, 4, 5. Okay. So absolute max at 2. So the function is going to have to pass through here. This will be the absolute max, but this is also going to have to be a local max, but that's still fine. We can still satisfy the requirements, right? There's no way we can make this a global max, but not a local max, unless it's an endpoint, and it's not an endpoint. Okay, absolute minimum at 5. That's going to be an endpoint, so we'll put that here. 4 is a critical number, but there's no local max or minimum there. What does that mean? So a critical number is where the derivative doesn't exist or the derivative is equal to 0. We can't have a critical number and no local max or min when, like, at a discontinuity, right? At certain discontinuities, the derivative doesn't exist, but it could also be not a local max or min. Like, for example, so here the derivative doesn't exist. It's a discontinuity, but actually this actually is a local max. But you can see how at a discontinuity you can make a function to where it's a critical point because the derivative doesn't exist. And it also happens to not be a local max or min either. You know, maybe the function doesn't exist here, right? If you put a hole here, well, there you go. That's a critical number. The derivative doesn't exist here. But this is not a local max or min either. But one of the requirements is the function is continuous on 1 to 5. So we can't do a discontinuity. So it has to be continuous. Now, we can have a continuous function where the derivative doesn't exist. So that would be a critical number, right? That's like this, for example. Here's a continuous function. The derivative doesn't exist. So that's a critical number. But there's no way to construct a kink like this without it being a local max or min. The only way we can construct a continuous function that has a critical number at that continuous point, but it's not a local max or min, is like something like this. Here, this is a critical point because the derivative, it does exist and it's equal to 0, but it's not a local max or min. So it'll be something like this. Right? Let me redraw that. There we go. Okay, well, it'll be like, so we could do this. We could say, let's make this like that. We could do a smooth point here, like a, well, yeah, okay, we could do that. Let's do function exists here, and then like that. Derivative, this is a critical point, but it's not a local max or min. All right, find the critical numbers of the function. So finding critical numbers is easy. You just take the derivative and then find the points where the derivative is equal to 0 or the derivative doesn't exist. And that is it. That's it. Then you're done. But just a reminder, critical numbers, just because you have a critical number, it doesn't mean that that critical number is going to be some sort of local max or min or global max or min. It just has the potential to be a local or global max or min. But for these questions, we're not concerned about local maxes or mins or global maxes or mins. They're just asking for the critical numbers. That's it. So this is straightforward. Find the points where the derivative is equal to 0 or it doesn't exist. That is it. That's all we're doing here. Okay, what's f prime of x? 1/3 minus x. All right, 1/3 minus x, where does that equal 0? When x is equal to 1/3, is there any point where this doesn't exist? No. So that is the only critical point. That's it. That's all we're asked. That's all the question's asking us. X is equal to 1/3 is the only critical number of the function. All right. F prime of x is equal to what? 6x squared minus 6x minus 36. Set this equal to 0, solve for x. Let's factor out a 6. Let's factor this. So x is equal to 3 and x is equal to minus 2. All right? Those are two critical numbers. That's where the derivative is equal to 0. But is there any point where the derivative doesn't exist? No, this is a polynomial. So these are the only two critical numbers. Okay, what is g prime of t? And this is plus. Okay, let's set this equal to 0, factor out a t. Okay, so t is equal to 0 is a critical number. Now, can we factor this? All right, so we've got 8. 4 times 2 is 8. 2 times 2 times 2. So really 4 times, well, or no. Okay, so we can't factor it. Let's use the quadratic formula, right? We're solving 4t squared plus 3t plus 2 is equal to 0. So t is equal to minus b plus or minus b squared minus 4 times a times c all over 2a. 9 minus 16 times 2 is 32. So this could be a negative number here. This is going to have imaginary solutions. So we're not including imaginary solutions. So, okay, is there any point t where the derivative doesn't exist? No, this is a polynomial. So this is the only critical number. Again, in the upcoming problems, we're going to get into what do we do once we have a critical number? What do those critical numbers mean? Right now, this is just what are the critical numbers? Don't overthink this. Where the derivative is equal to 0 and where it doesn't exist, that is it. That's the only thing a critical number means. Okay. We've got 3/4 t, so 3/4 minus 1 minus 1/4 minus 2 times 1/4 is 1/2. T to the 1/4 minus 1 is minus 3/4. Okay, so this is 4t to the 1/4, and that's under 3, and then 2t right? So, first of all, where does this not exist when t is equal to 0? So that's a critical number, and there's no other point where it doesn't exist. Now, let's set this equal to 0 and solve. So, 3 over 4t to the 1/4 is equal to okay, so cross multiplying 6t to the 3/4 is equal to 4t to the 1/4. All right, let's divide both sides by 4t to the 1/4. So, okay, we've got, so t to the 3/4 minus 1/4. We've got 3/2 t to the 1/2 is equal to 1. So t to the 1/2 is equal to 2/3. All right, now we square both sides, and you get t is equal to 4/9. And t is equal to 0. Those are the critical numbers. Well, actually, technically, since we squared both sides like this, we need to check that this is actually a solution. So, right, that's what you do with radical equations. When you have to, with radical equations, since sometimes you're squaring both sides or taking an even power to both sides, you can have extraneous solutions. So, all right, if we do, okay, we got 3/4 times x to the minus 1/4 minus, well, let's do this. 1/2 times x to the minus 3/4. Now do this minus this. So now we've got, well, okay, let's say this with x is equal to 4/9. 0. So there we go. Okay, so f prime theta is minus 2 sine theta plus 2 sine theta cosine theta. All right. Is there any theta that where this doesn't exist? No, because sine and cosine are, there's the domain is all real numbers. Okay, now let's set this equal to 0. So you've got 2 sine theta is equal to 2 sine theta cosine theta. So we've got, let's see, we divide both sides by 2 sine theta. You get cosine theta is equal to 1. Okay, so cosine theta, if we do this in radians, let's do this in radians. So, because we're doing derivatives here. So, when we're taking derivatives of trig functions, then you can still do that in degrees, but the way it would be different. Like you got to be careful with that. We took these derivatives, and the way we took these derivatives, we assumed that the theta was in radians. If we assume that this is in degrees, we have to, the derivatives would be different. So just saying sine, or just saying cosine of theta, 2 cosine of theta is minus 2 sine theta, that implies radians. So we got to be in radians here. So we're in radians. Inverse cosine of 1 is 0. But it's not just 0. It's really like 0 or 2 pi or 4 pi or 6 pi, right? So theta is equal to 2 in pi, where n is greater than or equal to 0. So n could be 0, or if n is, or n could be 1, so 2 pi, or n could be 2, so 4 pi, etc. Now, actually, I did this wrong. I messed this up. So you can't. There's missing solutions here, so you got to be careful, right? What did I do wrong? When it comes to solving, like remember when we solve like polynomial equations, you want to really you want to be careful when you divide both sides by something, because you could be missing solutions. You want to like factor as much as you can, like in general, as much as you can. So here, let's factor out a minus 2 sine theta. So we get what? 1 minus cosine theta. So 1 minus cosine theta is equal to 0. That's what we just solved. So theta is equal to 2 in pi. Or minus 2 sine theta is equal to 0, or which is sine of theta is equal to 0. This is theta is equal to n pi. So, right, either or. So we could just say theta is equal to n pi are the critical numbers, where n is an integer. Find the absolute maximum and absolute minimum values of f on the given interval. So for these problems, we're going to be working with continuous functions on closed intervals. And remember, the extreme value theorem states that if you have a continuous function on a closed interval, then there must be an absolute max and absolute min on that interval. All right, so how do we find those values? First, we find all of the critical numbers on the open interval from the specified closed interval. So in the open interval from 0 to 5. And they're just saying that because, you know, the derivative, you're not going to be able to evaluate the derivative at the endpoints. So you're just looking at that open interval from 0 to 5. Okay, then you find the values of the function at the endpoints, right? Because this is a closed interval. And then the largest of those values, the critical values and the endpoint values, is the absolute max, and the smallest is the absolute min. Okay, so let's do this. F prime of x, let's do those steps. 4 minus 2x, set this equal to 0, 2x is equal to 4, so x is equal to 2, and then there's no values where this derivative doesn't exist. So here's the critical number, the only critical number. All right, now f of 0 is equal to 12. F of 5 is equal to 20 minus 25. Okay, so now the largest of all of these three values is the max. Well, okay, no, we need to find the value of the function at 2 as well. So f of 2 is equal to, so 12 plus 8 minus 4, 20 minus 4 is 16. So now we're looking at these values. This is f of 2. The largest of these three values is the max, the absolute max. So f of 2 is equal to 16, and the smallest is the absolute min. So f of 5 is equal to minus 5. No. I got to put 12 here. This is 12 plus 20 minus 25. So 12 plus minus 5 is 7. So 7, 12, and 16, this still is the minimum. Okay, so there's the global max and min. Okay, so why does this process work? How do we know that this is for sure the global max and min? Why does the extreme value theorem work? Okay, so we've got a closed interval on a continuous function. The first thing to note is that there's a rule that we learned in the textbook section that if you have a local max or min, and we know that you can't have a local max or min at an endpoint. For a local max or min, you have to specify an open interval around the point. You can't do that at an endpoint. So if you have a local max or min, which is going to be within the interval, then that point also is going to be a critical number. Not every critical number is a local max or min, but every local max or min is a critical number point. Okay? The next thing to note is that, so for a continuous function, the only way you're going to have a global max or min that's not at an endpoint, that's within the interval. If you have a global max or min within the interval, that's also going to have to be a local max or min. Think about it. There's no way, unless it's not continuous, to have a global max or min that's within the interval. That's not a local max or min. Okay? And then then, but you could also have just the endpoint is just is larger than everything or smaller than everything, right? Just because that's the way it's defined. So what you do is you find the value of the function at the endpoints. That makes sense, right? And you're just going to compare the value of the function there to everything else you analyze. But then you find all the critical points within the interval. Now you might be saying, well, what if you have a critical point that's not a local max or min, right? Like we did, like something like this. Well, it doesn't matter. You're going to find the value of the function at that point, and you're going to compare it to all the other values you found, and it's not going to be larger or smaller than everything, right? We're not analyzing the behavior of the function at these critical points. We're just analyzing the value of the function there. Because if we've analyzed the value of the function at the endpoints and all of the critical points, then we know that since the function is continuous, we know that there's no value that we didn't analyze where the function can be bigger or smaller than what we've already analyzed. Because there's no way you could have a value of the function that's bigger than what would be found at the critical points. Okay? So same process. Let's find the critical points. So right? There's no points where this equals to 0. This is a polynomial. No, there's no points where this doesn't exist. So now where is this equal to 0? We've got x squared minus x minus 2. So x is equal to 0 as a critical point. And then can we factor this? We've got x, 2, 1, minus 2 plus 1. So x is equal to 2 and x is equal to 0. All right. So now we need to find what is f of 0, f of, well, okay, we already got 0. So, all right. What is f of 0, f of 2, f of minus 2, f of 3? So f of 0 is equal to 1. F of 2 is equal to 2 to the 4th is 16. 16 times 3 is 48. Okay, 2 cubed is 8. 8 times 4 is 32. Okay, 2 squared is 4. 12 times 4 is 48 plus 1. Okay, so f of 2 is equal to 48 minus 48 is 0, minus 32 plus 1 is minus 31. All right, f of minus 2 is equal to, so 48, but now we're going to get minus 2 cubed is minus 8, minus 4 times minus 8 is so plus 32, minus 48 plus 1. So f of minus 2 is equal to 33. All right, now f of 3 is equal to, let's use the calculator here. So 3 to the 4th times 3 minus 4 times 3 cubed minus 12 times 9 plus 1, 28. Okay, so the max, f of minus 2, the min, f of 2. There we go. Okay. Same process. We've got 1 minus t to the 1/3. So 1/3 t to the minus 2/3. Okay, so this is 1 minus, so 3t to the 2/3. Okay, so a critical number here is 0, right? Now, where does this, that's where this doesn't exist, but where does this equal to 0? Is there a point where this equals 0? So 1 over 3t to the 2/3 is equal to 1. 3t to the 2/3 is equal to 1. T to the 2/3 is equal to 1/3. 3/2, 3/2. So t is equal to 1/3 to the 3/2. Okay, so let's do this to make this easier. Let's say we've got x, x minus x to the 1/3. All right. We'll say store this as e. Okay, so now we want to evaluate e with x is equal to 1/3 to the 3/2. Okay, so there we go. There's 1 point. Now let's put in x is equal to 0. There's another point. Now let's put in x is equal to -1. There's another point. Now x is equal to 4. All right. So, okay, this is negative. This is positive. So there's your maxes and mins. So the max is f of 4 is equal to 4 minus 2 to the 2/3. The min is equal to f of 1/3 to the 3/2. And that's minus 2√3/9. That is the global max and min. Okay. Derivative of the, let's take the derivative using the product rule. So derivative of the first times the second plus derivative of the second times the first. Okay, so what do we have here? Okay, we're on this interval, and so actually if we come back to this problem, we didn't need to analyze like t is equal to 0, because that's not on the interval, right? I don't know if I did this. Yeah, we analyzed, I didn't need to do f of, oh no, we did need to do f of 0, f of 2. Yeah, so I'm just saying that I didn't need to we didn't need to evaluate f of 0. Well, no, we did. That's part, that is on the interval. So if you happen to get a critical number that's not on the interval, then you don't need to analyze it. All right? And I'm saying that because here, x is equal to 0 is a critical number. And also, like, the natural log of x doesn't exist for 0 or negative numbers as well, but that's not on the interval. So it doesn't, so that's not part of the analysis. All right, so let's set this equal to 0. We've got minus 2 natural log of x plus 1 over x cubed is equal to 0, which means that you've got 2 natural log of x is equal to 1, right? Because we just need to solve for when the numerator is equal to 0. So natural log of x is equal to 1/2. Raise both sides to the e power. Or no, raise both sides to e. So you've got x is equal to e to the 1/2. Okay, so x to the minus 2 times natural log of x, all right, this with x is equal to e to the 1/2. So 1 over 2e. F of e to the 1/2 is equal to 1 over 2e. That's the only critical number. So what about f to the 1/2? We're going to evaluate the endpoints. Minus 4 natural log of 2. All right, now what about f of 4? Natural log of 2 over 8. Okay, so what is bigger, 1 over 2e or natural log of 2 over 8? This is the min, right? Now, what's the one of those two is the max? So we'll say this minus this. Oh, come on. Is a negative number. So this is the max. This is larger. This is the max. Okay. This derivative, let's find the derivative. So chain rule. It's 1 over this times the derivative of what's on the inside here. So that's going to be 2x plus 1. All right. Where does this equal 0? When 2x plus 1 is equal to 0. So when x is equal to minus 1/2. Where does this not exist? When x squared plus x plus 1 is equal to 0. And is this on the interval? Yeah, this is on the interval. So can we factor this? No. So let's use the quadratic formula, minus b plus or minus b squared minus 4 times a times c over 2a. 1 minus 4 over 2. Okay, this is going to be a negative. This is going to be a imaginary number. So we're not worried about any of this. So f of minus 1/2, f of minus 1, f of 1 is what? So we've got natural log of x squared plus x plus 1 will store that as e. Okay, e with x is equal to minus 1/2 natural log of 3/4. Okay, minus 1, 0. Natural log of 3. Okay, but natural logs of numbers less than 1 these are negative, right? So, and then greater than 1 are positive. So this is the min, and this is the max.